Hi friends, today we are discussing our paper named Hardware Software Co-Design of an Embedded Power Management Model with Adaptive On-Chip Power Processings. Myself Pankaj Vanade and I'm with Raghunath Reddy. In this paper, an embedded power management model with an adaptive on-chip processing scheme which is developed for the next generation VLSI systems. The model comprises a single inductor multiple output power converter, that is SIMO, and the software defined the digital controller. By using a digital control, the entire converter can be integrated with the microprocessor units, that is MPU. This enables a hardware software co-design and which is effective the power processing carried out at the software levels and can be directed to generate the most optimal voltage at the hardware level. The embedded power management model leads to an integrated and autonomous system on chip, that is SoC design, which is independent and additional external hardware unit. In order to achieve the optimal performance in this power system, equally advanced power management techniques are urgently required. One such technique is the dynamic voltage scaling, that is DVS. This technique is refined to tune in on voltage and frequencies of the operation that allow you all the process in the modern computing systems to complete just in time, that is within a time. As these techniques minimize the power dissipations under the presumption of the exploiting multiple or variable power sources, such an implementation would traditionally require many individual power converters. This leads to a bulky architectures due to the use of large inductors and the introduce the serious EMI noise and the large power switches that lead to significant silicon cost. Therefore, the model consists of software-defined integrated single inductor, multiple unit, multiple output, and the step-down power converter and the digital converters. The online power processing that is executed in the software control determines the exact voltage to be delivered at the hardware level to achieve the joint improvement in the power, energy, and performance. The digital implementation of the control also enables the process scalability, therefore ensuring that the design can easily be transferred for the future technology generations. And designed with 120 nano CMOS process, the converters precisely provide the three independently variable power outputs from the 0.9 to 3 volt with a total power range from the 33 to 900 megawatt. This is a very fast load transient response of a 3.25 microsecond is achieved in response of the 67.5 milliampere full step load current change. Now remaining part will be explained by Raghu.
Yes, this is the system architecture for this paper. In this SIMS power converter, this diagram shows this diagram for to overcome the drawbacks addressed in the section converter in embedded power management model. It features a step down power stage with multiple and variable outputs and a digital feedback controller with embedded software control algorithms to power integrated digital VLSI systems such as multiple core processors, memory and input output, etc. For design of the controller, three software-defined controls work jointly with the power stage to ensure efficient power and energy minimization. During the startup period, a parallel startup mode is adopted, wherein the power stage is automatically reconfigured into the bulk topology. Power is delivered simultaneously to all three outputs. In steady state, online power sensors continuously monitor the instantaneous power demands of the output loads as well as the input power. The sensor power is then proceeded to determine total power demand along with the priority of power delivery to each of the outputs. The digital adaptive power allocation controller then utilizes the sensed and proceed information to decide on the power delivery schemes. It then appropriately controls the power stage and thus amount of the power delivered to the each load in the system. And leading to efficient and fast robust system operation. The software defined controls can be pre-programmed into the general purpose microprocessor units and when integrated with the power stage and leads to realization of autonomous system on chip design for power management modeling. And then next, these are the adaptive and global control power allocation control. Here in figure A, it will show light load module. When all loads are light, the indicator is charges only once in global switching cycle with the energy of total load demands. This energy is then accurately discharged to load once at time. Switching power and noise will be reduced due to less frequent switching actions. And figure B shows a heavy load mode. In this mode, all loads are heavy, and the use of the previous scheme would lead to high peak currents and noise spikes. Instead, the indicator is charged and discharged based on individual load demands according to the regulation priority that is determined online. Here, figure C shows unbalanced load mode. In this unbalanced load mode case, loads are heavy but loads M and N are light. Under this situation, the regulation only focus on power delivery for loads. The skipping operation on M and N reduces the switching power loss and noise and improves the response time to more power demanding loads. At a worst case load transit scenario is in case D. Here we will show emergency load mode. This is a worst case load transition scenario. In this scenario, the functional operation of load N without compromising the performance of others. An emerging switching capacitor power path is used to power load N. This switching capacitor power path is reconfigured from the temporarily unused components in the SITO converter. For example, energy can be diverted from the power capacitor supplying a non-critical load to the high priority application that develops sudden power on demand. Meanwhile, power application and priority will be redefined immediately, adapted to the change. This is online power sensing and processing diagram. Here we proposed in this paper the online power sensing processing circuits are integral parts of the software defined adaptive power allocation control. The power sensor consists of current and voltage sensing circuits along with the digital multiplier to determine instantaneous power demands as shown in figure 1. The sensor outputs are currents converted into respective frequency values, and voltage to frequency conversion is achieved using ring oscillator, while current conversion is achieved by using transistor. Scaling is based on current sensor followed by subsequent current to frequency conversion. The magnitude of the sensor currents determines the charge and discharge rates of the capacitor, thereby controlling resulting frequency. These frequency values are then utilized by the digital multiplier to obtain instantaneous power demand of the each output. Here all I2F converter and VTF converter and the usage of this online power sensing and processing circuit. Here I will tell I also read all those things before, and the final conclusion of this paper is we propose embedded power module consisting of adaptive SIMO step up and down DC to DC converter with on-chip processing schemes. The adaptive global local power allocation controls allows the converter to operate with supervised line and load and device regulations while keeping cross regulation at very small value. And the software defined digital controller enables the hardware and software co-design for on-chip power supplies, leading very competitive power management solution. This software defined digital controller, which gives the power management solution based on hardware software co-design for on-chip power supplies, hardware power supplies. Thank you.